here's a very, very famous radioactive sample, okay? And we're going to talk about carbon 14. And carbon 14 is so important. Carbon 14 is used to date the times of early humanoids or humans, because scientists believe that humans arrived around 50,000 years ago. So carbon 14 is the element with its half-life that allows you to measure 50,000 years into the past. So that's why carbon 14 is super important. And so what do we know? So carbon 14, which is typically written like this, is a radioactive isotope that is unstable. And so what we see here is that if it undergoes beta decay, here's what we're going to see here. So if I have carbon 14, and now it's going to go beta decay. So I'm going to change colors here so it's nice and clear. So I'm going to say, here's my atomic number. And then I'm going to choose the atomic number to be, I think I messed up. 14 is the atomic mass, 6 is the atomic number. So now what does it do? It goes beta. And as it goes beta, what happens? The atomic mass, look what happens. The atomic mass does not change. So if the atomic mass does not change, it stays at 14. And then it says the atomic value increases by 1. So if I look at this, then the atomic number has to increase by 1 like this. So now I have a different atom. And then at the same time, it emits beta, and then it emits energy. So then the question is, what's this? So then we look at the periodic table. So that means when I look at this, I have 14, 7. So then I look at the periodic table, I'm looking for atom number 7. So if you look on the periodic table and you find it, here we go. It turns out to be nitrogen. Okay, it turns out to be nitrogen. So now, what does this tell us here? So if I look at the reaction, so then the reaction shows I have 14, 6 carbon. It goes beta decay. And then what do I get? I get 14. And now I have 7, which changes the element. And I get this beta minus plus this energy here. So when you look at this thing, it's clear what has happened. And once again, even though I've already said it, I'm going to say it again. So the number of neutrons decreases by 1. The number of protons increases by 1. And because of this right here, right? If the number of protons increases, this changes the identity of the nuclei, right? So it changes it, just like alpha particles changes it. So now let's sketch this thing here, okay? Let's sketch this thing. And the sketch is slippery, okay? The sketch is slippery. So let's see if I can do a good job with the sketch. So if I look at this, let's look at the number of protons and neutrons in carbon and in nitrogen. So if I have 14,6 carbon, immediately we see that we have 8 neutrons, 6 protons. And then if I look at nitrogen, we see that we have 7 neutrons, right? It decreased by 1. And then you could see here that the number of protons increased by 1. So again, that's exactly what you're seeing here. You know, maybe I should have done a better job of this. And I think what I'm going to show here is that I'm going to move this over a little bit. And look, actually, I think I might move it a little bit more. And what I'm saying here is this, right? Look at this guy. Decreases by 1. This increases. So if I look at this next one here, you see that this increases by 1. That is a beta decay. Now, what's the picture like? So the picture is slippery. Okay. So what I got to do here is that let's do counting. Okay. So I'm going to try to count. Okay. So here's my nuclei now. And what do I have? I have 6 protons. Let's draw 6 protons in here. So I'm going to go 1, 2, 3, 4, 5, 6. So these are my protons here. And so when I'm looking at my protons, I want to be careful how I count. Now I'm going to isolate 1 neutron. Here I go. So this is going to be my 1 neutron that I'm going to isolate. So I need 8, so that's going to be 1. But typically I draw them blue. So this is 2, 3, 4, 5, 6, 7, 8. So remember, this guy right here, this is the neutron that decays to a proton. So what happens then, again, we have the magic, right? It spontaneously decays. It's like pulling a rabbit out of the hat. And so what happens here is that the nitrogen is the really big one here. So what I'm going to do here is that I'm going to copy this guy here. And I'm going to go put this right here. So suddenly there's a new atom. And what I'm going to do here is that instead of yellow, it changes, and I'm going to draw a green. And that green now becomes the extra proton. Okay, so then this green right here, this is the extra proton. So it loses a neutron and it gains a proton. But remember, what is the actual decay? The actual decay is what? I get a proton. So then the neutron is ejecting what? A beta particle and energy. So I got to focus on that proton right there. So if I focus on the proton, part of this thing goes like this. It ejects out a beta particle. Okay, for right now, let's call this beta particle this purple particle. So this guy gets ejected out of this region, and this is my beta minus. And at the same time, there's this energy that gets ejected. And so now I have this glob of energy that gets ejected, which looks like this here. That is a beta decay. So now what we want to do here is that we want to go in and we really want to look at this. So once again, maybe I should write this off to the side here and say, once again, a neutron within the nucleus has changed itself into a proton and emitting a beta and energy. Okay? That's what beta decays do.